Welcome everyone to our coffee Zoom today, and I am going to talk about transceiver troubleshooting. So there are so many things, like Priya mentioned, that I break it down into two parts. Today I will cover the first one, which is, you can see it from the list, mux and demux, or the 4-link data, right? Because since our focus is on 40G and 100G, yeah, those two products have 4 data link coming in and getting out. Second is I will talk about transmitter optical eye, and also their optical spectrum, and also to utilize the DDMI to do some troubleshooting. And last, and if we have time, I would talk about some basic receiver sensitivity measurement. If not, I would save the receiver sensitivity measurement until next time. So part 2, as you can see, I talk about other things, more registers, CDRA, CDR, LOS, LOL, data squelch, and some advanced receiver sensitivity measurement. So to start, and here's a block diagram of very standard CDR people use in transmitter or in receiver. As you can see from the block diagram down there, the same IC can be used for transmitter as well as a receiver. And the interface for 40G, like I mentioned the last time, is 10.3 gigabits per second. And for 100G is 4 times 25 gigabits per second, CoW4. So you can see the circle I put on, highlight mux and demux, because and I think in order to be very good in understanding the transceiver, we must explain the mux and demux function, and you will know why. So the next picture shows you exactly how the transmitter eye looks like when it's demuxed, that is, and how the transmitter spectrum characteristic is. You can see there are 4 lambdas there, right? So it represents 4 links. Each one is called channel 1 to channel 4. If you use the name like a link, it will be link 0 to link 3. That's, by the way, the link is from the IC people. So when you use the IC, you talk about links. So in order to do a demux, and I list on the right-hand side, the register at page 0, 56 hex. If it's 00, all the transmitter, all 4 transmitters are all on. When it's FF, all off. When it's OE hex, that is, only link 0 is on. OD is link 1. OB is link 2. 07 is link 3. So that's how you can control, so to speak, how to demux those 4 channels one by one. Some of you might already know about it, but some of you might not. So I just share with you my experience how to troubleshoot transceiver. This is a good way to do it, because this is from the MSA table. Everyone can change it. It's allowed. So the next page shows you when you don't demux, you see noise, basically. So I want to explain why this is so blurry here. because I wanted to look at 25G per second, but however, my scope only can go to 10G. So I decided to change the PHY of the whole system, so it can run 10.3 gigabits per second instead of 25 gigabits per second to allow me to look at I. So that's one of the way, because we all have old equipment, right? So this is very appropriate to do that. Instead of buying the new 25G compatible scope, you can use whatever you have, 10G, and you can also do that. The only trick is you have to change the PHY setting, but it's very straightforward. So you can see on the upper right-hand side, it's been changed to 10.3, right? So you can also see in register 56, it's all 00, that means all links on. It is exactly like that. So you don't see much. In fact, it looks like a PAM signal, but it's not because all 4 links are muxed together. So down there, you can see I start to demux one by one, right? When I do OE, and the scope only has link 0 and OD, link 1, OB, link 2, and O7, link 3. Now, this is a pretty respectable eye. Looks like it might have the optical filter on it, right? 10.3, but I'm not sure on this. On the next page, I want to show you exactly what's happening. This is, let me show you with the DC level. When you have DC level, you see exactly what's happening on optical power. So on this one is the same. This one, later on, I found a better scope. This one is like a 25G scope, but the data I still run at 10.3 in order to troubleshoot, right? So you can see with all channel on, and it's like that. So I did not change any scaling. On this page, when I change the, when I do the demux, and all the settings remain the same. So you can appreciate the DC level, right? So you can see on channel, on link 0, the modulation is a little bit less, but it dropped down to this level, right? Instead of up here, you drop down here. Link 1, link 2, and link 3. Link 3 looks like it can be modulated better. It has a better laser, basically. So the next page, I will show you. This page, I show you the good one. Now, so all 4 links are okay. There's nothing wrong with it. All 4 eyes are perfect, all right? So the eye mask margin is between 30 to 40, roughly, right? It's a CWDM, ERB type of transceiver. Let me go back to here. Now, I want to show you a bad transceiver. So this transceiver, you can see it's a CWDM4, and it has a 1-channel band. The link, we call it link 2, which is channel 3. And coming back, and if you pay attention, this is a basic troubleshooting step. Immediately after I got this sample from the customer, they complain flopping, it doesn't work. So, but the first thing I want to find out, which channel does not work, right? So not instead of it's all 4 channels. It's very hard to troubleshoot. So the first thing I did was to do a optical spectrum scan, just like this OSA, right? You scan it. The span itself is 80 nanometers because I want to capture all 4 of CWDM channels. And keep in mind that this parameter is very important. The resolution, 0.05 nanosecond So you need to use the very fine resolution to look into the detail. And I scan it immediately. I identify link 2 is bad, right? You can see it now. I can see what we call the SMSR issue, right? Some of you might know SMSR stands for simul suppression ratio. That means the simul is pretty high. See, this is supposed to be the simul. It's very, you can see the signal to noise ratio is 42, right? 42 dB. Hair to hair is at least 42 dB. But hair to hair, you can see it's about 13 dB, right? So the simul becomes very bad. So, and the other thing I want to show you is the peak of the spectrum, optical spectrum analyzer. It's the true power. When you measure the power using an optical power meter, the power shows depends on the filter bandwidth that you have, right? So you understand, integrate everything below the bandwidth. So, but on the optical spectrum analyzer, the peak power shows exactly the peak power is. It does not capture whatever area down here, right? So it's much more accurate. So you can see the peak power here, it dropped to 8.9 dBm here, right? So you can see about 4 to 5 dB down compared to all the rest of them. So, and I want to point out the signal to noise reading is a very accurate measurement and the resolution. So one more thing to point out, if you use the optical power to measure individual power by disabling the rest of the signal like I did, and I put it back down here, minus 2.4, minus 1.6, minus 2.08, minus 0.9. This one is very hard to say is good or bad, right? You cannot see it, but on the optical spectrum analyzer, you can see immediately it's bad. So what I'm trying to tell you is, optical spectrum analyzer is a very good tool to identify problems in a transceiver configuration like this, like a 40G, 100G nowadays, 400G and so forth. As long as they mix together, you can see them clearly. You scan one, you know immediately what's wrong. So on the left-hand side, I also disable the other 3 links to show you the optical eye. True enough, link 2 has no eye because you can see the optical power drop. There is the modulation is down to 1, right? Basically, it's modulated noise, basically. So you can see the confirmation comes from the CDR, not CDR, the scope itself, the CDA. Okay, so the next one is another example, but this one is link 1. You can see the single simul suppression go to trash. You can see, and the same thing I want to point out, the optical power measurement by the optical power is not very accurate, and sometimes you cannot tell it's good or bad by measuring the optical power, because the rest of the energy, the optical power measure, become a second mode, so it's useless as far as the modulation is concerned. So I just want to point out that, and the next one, I just want to, you might not be interested on the next one, but I just want to point out, when I do a span 10 nanometer apart, this one is 18 nanometer scan. This one is 10. So you can truly see what is become of the laser, this one and this one. And I want to emphasize, laser will die sooner or later. It depends on how long, right? So there are two disadvantages of using fiber optic. There are many advantages using fiber optics, but there are two issues. One is the temperature, right? Extreme temperature will change the laser behavior, right? That's one. Second one is the laser will degrade. When it degrades, it becomes like this, right? It's channel 3 on the first one and channel 2 on the second one. It becomes the simul suppression becomes predominant. So that's one of the way to capture them by using the optical spectrum analyzer. And this slide I showed last time, I just want to place it here to get your attention. So, and here also, because there are two parameters down here I want to mention later, which is the transmitter power and receiver power. So when you do, that might be the last topic I talk. So I say the sensitivity next time, but I still want to mention this. This is captured by from a switch, 32-port switch, 100G switch. And you can see all the register value displayed here. So the first thing I would do is to translate it by using the formula. I put it down there, right? To put in the Excel to translate to different values here, right? You can see on the transmitter, there are 4 power, but when you add it together, it becomes this one. This is exactly how you should measure with using a power meter. It's very accurate, this measurement, by using this. This is in dBm already, but when you want to add together, you want to convert it into milliwatts, and then add them together and convert it back to dBm. Likewise, on the receiver, you do the same thing, and you can, when combined together, the total combination is like a -8 here. You can see there's about 15 dB attenuation already. I put an attenuator here. And I will save this topic later on, next time, as I show here how to do a proper sensitivity measurement manually. What it means by total optical power or by individual optical power, and how to calculate manually the bit error rates, what makes sense. And I think I will save it until next time together with the other stuff. I want to ask if you have any questions for me that I can answer. I already see 3 questions here. I would like to read it out loud. The first one is, are we going to be included in automatically for the second part? Yes, you will be. Priya will send out invitation. Second one, will we be getting a copy of the slides? Yes, ask Priya. Priya would send out a PDF version, I believe, to you. The third question is, what is the main reason behind a bad spectrum? Why only one wavelength is affected in some cases? All because there are 4 individual lasers. There are 4 lasers, they all operated independently. They're all modulated independently. So in order to troubleshoot, you need to separate the other 3 to isolate one to troubleshoot, right? So the best spectrum show you one of the main failure mode in fiber optic transceiver, which is, like I said, laser will die sooner or later. Some of them die in 1 year, some of them die maybe in 10 years, but all of them will die. So in order to identify how, for instance, there are other problems, other issues on the transceiver line, I2C, like the data, like the I mask margin, those are different types. But this one shows you one of the big problems, of the laser transmitter is the aging effect. So yeah, when the laser dies, sometimes the whole wafer, if they don't screen the whole wafer properly, you know, each wafer can produce like 2,000-3,000 of laser. The whole lot will die. So I have seen this happen. When it died like the whole group die. So that's the motivation why I talk about laser. Yeah. So are there any other questions?
Eric, I think there's one more.
One more, let me see.
Model number of the OSA.
Oh, okay, yeah. What is the model number of the OSA used? And I will send that answer to Priya. I don't know yet. I need to take out my old file in order to find out. This is, I saw that there are a lot of used ones on eBay on this one, but it's very old, but it's very powerful because this one is designed for mux and demux. All the default settings, you don't have to do much. You just turn it on. It display almost as the same as what I display. It's very nice. I like it, but it's very old. Some of them are dying, like a laser. Basically, the displaying is dying, so it's very dim. So, but however, I send this model name to Priya. You can communicate with Priya. Okay, Priya.
Yeah.